Okay, let's get started. So this week we're going to be talking about hierarchical models, and like every week we have to talk about the fact that I'm an employee of Columbia. Columbia develops stands for business purposes that creates an appearance of a conflict of interest, and perhaps this disclosure of conflict of interest policy is less inapplicable this week than most weeks, because insofar as businesses are interested in using Bayesian analysis, it is almost always to do hierarchical modeling. For example, companies that are interested in marketing are really interested in coming up with marketing campaigns that are geared toward individual consumers of whatever it is that they are trying to sell, and basically interested in estimating individual specific parameters and finding out, does this person have a parameter that makes them, more sensitive to an offer of a coupon. And so, you can have a web-based marketing strategy that, pops up coupons to people that you've estimated to be, much more likely to buy your product if they see a shiny, blinking coupon thing in the margin of the web page that they're visiting. And so marketing, although not very quantitatively sophisticated, is definitely interested in these hierarchical models that allow you to estimate individual specific parameters. And there was a book came out probably more than 10 years ago now called like Bayesian Methods for Marketing that really introduced these sorts of things in economics and marketing. There's also our package called Bayes-M that goes along with that book. I think all of the methods that they use for MCMC sampling of such models, such as Gibbs sampling, Metropolis Hastings, have been subsumed by Stan, at least theoretically, even though a lot of people who just, the only thing they've read is that Bayesian marketing book, are still using these not very good samplers to estimate models that are legitimately of interest to them. Anyway, we'll get into that more as we go along today and on Thursday. So what are hierarchical models? From a Bayesian perspective, at least, a hierarchical model is nothing more than a model where the prior distribution of some parameter depends on another parameter, and you want to estimate both of those. So from that perspective, it's just another application of the general multiplication rule, where your prior on some parameter is written conditional on another parameter, and that other parameter has a marginal or a conditional prior, and you multiply all those together, you get a joint prior distribution for all of the unknowns. And we already have seen an example of this, actually several of them over the course of the semester, even if we didn't explicitly talk about them as being hierarchical models as such at the time. But the paper homework assignment we did on traffic stops in North Carolina was an example of a hierarchical prior, or a hierarchical data generating process. There were police department parameters in particular police departments that depended on the overall North Carolina level parameters. And at the same time, there were individual specific parameters that depended on parameters for people of that race. And so you had different parameters for whites and blacks and so on. And all the way down, it was really a 4 or 5 level hierarchical model before you finally got to the latent probability that the person who was stopped was actually carrying something illegal. And from a Bayesian perspective, even though We only drew from the prior predictive distribution at the time. Clearly in the paper, they were also drawing from the posterior distribution of that model in order to make their conclusions. And so it was entirely possible for them, them being experienced users of STAN, to get this joint distribution for probably thousands of different parameters that were specified in this model with hierarchical priors. So that was one example. But even the bowling example had this hierarchical flavor to it. You could think of this as hierarchical likelihood if we actually had any bowling data where the number of pins knocked down on the second roll of a frame of bowling depends on the number of pins knocked down on the first roll of a frame of bowling. And it was much easier to compose a bivariate distribution for what happens on the two rolls in a single frame of bowling by composing it as a marginal probability density function for the first roll multiplied by a conditional probability density function for the second roll given the first roll. Now, in the bowling example, when we were first starting out, like the first or second week of the semester, we actually didn't have any unknown parameters. The only thing that was unknown was the data, how many pins you would knock down on this or that frame and this or that roll within that frame, etc. But the idea of decomposing a bivariate probability function into a marginal and a conditional was an important thing to learn as we were learning probability. But that concept, when applied to data or potential data, like the number of pins knocked down in a frame of bowling, can be applied, at least in Bayesian models, just the same way to prior distributions on unknown parameters. We can have a marginal prior distribution on the so-called first parameter and a conditional prior distribution on the second parameter given the first parameter. If we multiply those two PDFs together, we get a bivariate PDF for both parameters that we can then, multiply by a likelihood and maybe in some cases analytically work out what the posterior distribution is, but in most cases we can't, and we have to obtain draws from the joint posterior distribution that's implied by our hierarchical prior and whatever data that we observe. So the idea of a hierarchical model is very natural in a Bayesian setting. It's very common in a Bayesian setting. However, because most of the applications that you see in journals and the internet and stuff like that are frequentist, most of the discussion of hierarchical models that you're likely to encounter refers to the extraordinarily narrow circumstances in which hierarchical models can be estimated by frequentist methods, which we'll also talk about today. Now, if you go to a conference or something, you're very likely, or at least a general conference like APSA or something like that, you're very likely to see some person present the result of a hierarchical model that they use some frequentist estimator for, and they're very proud of themselves because they see themselves using something on the forefront of quantitative methodology, something that they can do that most other people who use frequentist methods can't do. And so they sound sort of ridiculous because if you talk to an actual Bayesian, they probably can't recall going to a conference and seeing a Bayesian presentation that wasn't a hierarchical model, because it's entirely reasonable to think that there's going to be variation in the parameters of whatever model you're talking about that vary. They're a little bit different for men than they are for women, or they're a little bit different for whites than they are for non-whites, or they're a little bit different from people who live in New York than people who live in Alabama. And so introducing these hierarchical structures where you're allowing the parameters to be a little bit different, but imposing some prior on how much they can vary across genders, across races, across states, across whatever grouping sort of thing you might think, or across police departments or counties or states or anything like that, is a very reasonable thing to do to try to capture the extent of the heterogeneity in the data generating processes that everyone sort of acknowledges must exist in the social sciences. And that is what really makes studying social science, whether it's economics or political science or whatever, different from, you know, perhaps other things in physics or biology, where it might be more reasonable to think that the same data generating process is really being, you know, applied to all protons or something like that. But even in biology, it's filled with hierarchical models, although not so much filled with Bayesians. So it's important to think that, you know, even though Bayesians were thinking about Bayesian models even before they had any real ability to estimate them. There's some very narrow circumstances in which you can derive the conditional distributions and come up with a Gibbs sampler. But even that didn't come to the forefront until like the 1990s or so. People were thinking, or Bayesians were thinking about Bayesian models, you know, from the time of Laplace, I imagine, even though it was, you know, not really possible to estimate those things. Around the same time, maybe in the 1980s or so, it became more within the realm of possibility to estimate some of these models from a frequentist perspective. And it really took off in a number of fields, sort of parallel with the development of MCMC stuff for Bayesian models. It wasn't really until Stan came along that you could estimate these models and get efficient sampling from the posterior distribution, not miss any parts of the posterior distribution. But that certainly didn't stop Bayesians in the early 2000s from estimating these models. And so now there's a pretty big literature from both a Bayesian perspective and a frequentist perspective on these models. So one example, talked about briefly, but I think we were running out of time and I sort of zipped through it, are these priors that impose a lot of shrinkage on particularly regression coefficients. So we talked about this day, we talked about Laplace priors and the fact that the lasso model can be seen as finding the posterior mode of a posterior distribution that used a Laplace prior on the coefficients and a normal likelihood for the observations. But a Laplace prior is really not that good, and it tends to yield, or it tends not to yield, posterior means and posterior medians that are close to zero, even if the real coefficient is pretty close to zero, when there's a lot of coefficients in the model. Now, lasso models get around this by not even finding the posterior mean or the posterior median, but just by finding the posterior mode, which may or may not be zero, and stopping there. But from a Bayesian perspective, if you have a lot of predictors and you want the coefficient estimates, or you think that the coefficient estimates tend to be very close to zero for almost all of the predictors, you just don't know which, you're going to want stronger priors that are more concentrated towards zero, but still have heavy tails, such that there's some possibility that one of your predictors is actually a really strong predictor. And Mike Betancourt wrote a case study, several, but this one in particular, about the so-called Finnish horseshoe prior, which I put a link to up here. And a Finnish horseshoe prior for a particular regression coefficient has this hierarchical specification. So the kth beta coefficient has a normal prior with the expectation of 0 and a standard deviation of tau times lambda bar k. And now we need, okay, what are our prior beliefs about tau and lambda bar k? So lambda bar k is equal to c times lambda k divided by the square root of c squared times tau squared lambda squared k. There's actually a space here, so those are separate. Okay, so this now, our beliefs about lambda bar k depend on c and lambda k. Lambda k has so-called half Cauchy prior on it, a standard half Cauchy prior with a location of 0 and a scale of 1. We haven't explicitly talked about the Cauchy distribution yet, but one way of characterizing it is the distribution is the ratio of two independent standard normals. So independent standard normal in the numerator, another independent standard normal in the denominator. What is the distribution of that ratio? And the Cauchy distribution has extraordinarily long tails, because as a ratio and the denominator has a normal distribution, standard normal distribution, there's considerable chance that the denominator is going to be pretty close to zero. Indeed, the median and the mean and the mode of the denominator is exactly zero. And anytime you divide some number by another number in the denominator that can be really close to zero, then the resulting ratio could be really negative, could be really positive, and the Cauchy distribution has that property. Indeed, the tails are so heavy that the expectation of the Cauchy distribution does not exist. So in the case of a Cauchy distribution over the whole real line, the median is zero, and you can define like an interquartile range and stuff like that. But the tails are so heavy that the integral that characterizes the expectation does not converge. And so we say the expectation does not exist. In any event, lambda k is the so-called half Cauchy prior on it, which means the absolute value of a Cauchy. So flipping the normal part over to the positive part of the real line. And then that leaves us a prior distribution on C. So you can think of the reciprocal of C squared as having a gamma prior, or you can think about C squared as having an inverse gamma prior. And we learned about the inverse gamma distribution last week. In any event, what are the parameters? Well, there should be a comma there. The shape of nu over 2 and rate, or probably scale, actually, of nu over 2 times s squared. Tau that goes into this expression here also has a half Cauchy prior, although you can choose a scale parameter TO, and you can choose what value of s to give. Now that is pretty deep for a prior that only pertains to one of your regression coefficients, but you can sort of see here that if the standard deviation in your prior for the kth regression coefficients is something that could be very dispersed, could be very concentrated, you have a flexible prior that it might be quite appropriate for regression coefficients. And the reason why that is the case is that it has both a so-called global scale parameter tau that applies to all of your regression coefficients, and a local scale parameter lambda k that is specific to the kth. So if the tau is small, then all of the betas are going to be really concentrated near zero. But even if tau is small, if for maybe 1, 2, or a handful of your parameters lambda k is very big, then all of a sudden the prior distribution for beta is very spread out, and you may get a posterior distribution of beta that is pretty far from zero. And so you can implement this prior in RStan arm by specifying prior equal hs, and it takes arguments for s and tau 0, maybe some other things, to specify a prior like this, which is very concentrated near zero but has very heavy tails. Becca.
So is one interpretation of this that tau is almost like the equivalent of a ridge parameter, like a ridge regression parameter that's just shrinking the overall size, and lambda is like more like the lasso, and that it's like making things zero?
A little bit. So if instead of having lambda k, we just had like all lambda k's were 1, then this would be a lot like ridge, and tau is your sort of overall ridge parameter. But this enhances that idea by sort of allowing 90% of the betas to be very close to zero because tau is small, but 10% of the betas not so close to zero because their associated lambda k's are sort of bigger than tau is small, and it gives it more room for those small number of betas to depart from zero. And you see this not so much in the social sciences, but definitely in regression models for like genetics and things like that. They may have like, 20 people or something in their study, and they're interested in a substantial number of like chromosomes or other biological things like that. And so they may have millions of predictors for some sort of genetic condition. They don't know which, mutation of which gene or whatever might be responsible for whatever condition it is they're studying. But they think it's, one of them or some combination of a few of them. They just don't know which ones. And so they're basically doing a regression with 1 million predictors. And you really want to put a hierarchical prior on that such that most of them, like maybe all but a handful of the million, are going to be really close to zero, and maybe 5 or something pop out that you could do additional study on to see if these mutations are actually the cause of whatever disease these people have. So this is one example of a hierarchical prior, but one that involves like 4 or 5 different things. It doesn't have to be that complicated. For example, interaction terms can be seen as hierarchical models. So suppose we wanted to draw from the prior predictive distribution for a model where the coefficient on the person's age is a linear function of the person's income, and we have some continuous outcome that we are interested in. So to define a function like to do that in the Stan language, we take an integer for the number of simulations S that we want to do, a vector of size n for income, a vector of size n for age. We compose, or we initialize our matrix to be S by n, and then we loop over the number of simulations that we want to do. We draw the intercept from a normal prior. We draw the coefficient on income from a normal prior. Obviously, you can choose different standard deviations or even different distributions for these coefficients here. And then gamma 0 and gamma 1 are themselves being drawn from normal priors. And then we compose a vector of size n, so one of these elements for each observation in our sample, of gamma as being gamma 0 plus gamma 1 times the person's income. And then what do we do with that gamma? Well, we use it to form the conditional expectation mu, which is intercept plus coefficient on income plus coefficient on age multiplied together element-wise. So each person's age is being multiplied by their respective gamma, and the gamma of the ith observation is gamma 0 plus gamma 1 times the income of the ith person. And so our coefficient on age is a linear function of the person's income. But if you just sort of look at this and do basic scalar algebra with just the distributive law, you can see that a particular person's mu is just alpha plus beta times income. And then you stick this whole expression in for gamma there and distribute age across. You get gamma 0 times age plus gamma 1 times income, element-wise multiplied by age. And you can see this is the form that an interaction model typically takes, where you have income, you have age, and you have the product between income and age. And gamma 1 is the slope of that third variable that you created by multiplying income and age together. Either way you do it, you have an equivalent expression for mu. You have, normal or not normal exponential prior with a mean of 5 on sigma, and then you fill in your matrix of prior predictions by taking the nth conditional expectation and adding to it a normal error with standard deviation sigma. Return this stuff out at the end. So Leif.
I actually have a question to the slide before. I wasn't sure about the interpretation. Usually, like the K refers to like how many coefficients we have in total.
So this is the coefficient on the kth variable. So like age or income or, you know, gene 2714.
Right. And so like it's not like they're not talking about, so say like different sets on different categories within one variable, and we are talking about actually different coefficients. So
Could go either way. But if you had, you know, you could do one of these for the coefficient on what state you live in, if you think of the 50 states as being represented by 50 dummy variables. This might be a little bit extreme for states because, you know, there's like a lot of variation by, you know, region and stuff like that. This might be shrinking towards zero a little bit too much in that context. But, you know, if you think about modeling like all your genes as predictors, then definitely you're going to want more concentration towards zero there. Ju.
So going to the next slide, so I'm like still not really sure what gamma. So like this is a hierarchical model, right? So
Yes.
what is that gamma quantity? How is that being distributed?
So gamma is the coefficient on age, but each person has their own gamma because this gamma is a function of the person's income, which is unique for every person. And so basically you have a linear model within a linear model. Gamma is a linear function of income with an intercept and a slope. And this gamma in turn is the slope for the age predictor in this model. So it's just the coefficient on age, but rather than being a constant for all people, like it would be in a flat model, we've now introduced the possibility that, you know, people who are, you know, both old and rich may behave, you know, differently than people who are young and rich or old and poor, that it depends on both of these things together.
What is the dependent, like what are we trying to show again?
Mu is not a prediction. Mu is the conditional expectation of the outcome. I didn't say what the outcome is. It could be anything that is continuous.
So age and income in this case are both.
They are predictors of whatever the outcome is.
Okay.
And the way we have set up this hierarchical model, we think that the coefficient on age depends on how much income you have. Marlon?
Based on the code here, two persons with the same income have the same gamma value.
Yes. You know, particularly if we use income categories, it's totally possible that you'd have more than one person with the same income and consequently the same coefficient on age. But the thing that I was trying to get you to see here is that this construction of gamma, where everyone has their own coefficient on age, is equivalent just by multiplication to what you usually see when you see people doing models with interaction terms, where they have income, age, and whatever the product of income times age is. But the way people usually do interaction terms by multiplying together income and age to be this third predictor is an overly restrictive way of doing a model like that. So what if the coefficient on age, so this should say the coefficient on age, is not an exact linear function of the person's income, but is rather a noisy, to some extent, linear function of the person's income. We could proceed in much the same way with the same alpha, beta, gamma 0, gamma 1, sigma, but we now have an additional parameter tau that comes into the data generating process like this. So when we loop over observations, we create the gamma for the person I as gamma 0, or person N actually, gamma 0 plus gamma 1 times the income of the nth person plus a random normal error in gamma, a random normal error in the coefficient for age. that is centered at 0, but has standard deviation tau. And now it's possible, or indeed guaranteed, that two people who have the same income, they don't necessarily have the same gamma. It can be a little bit different for one person than the next, even though they both have an income of $80,000 or something like that. And the extent to which this is a noisy function, is it like a little bit noisy or a lot noisy, depends on the size of tau, which can also be estimated, presuming that we have prior beliefs about tau to begin with. And so here I chose a prior on tau that is exponential with a mean of 0.25, which sort of reflects a prior belief that the coefficient on age, gamma here, doesn't differ too much from one person to the next that have the same income. But you know, they could easily differ by 0.5 or so. Then, okay, we have the gamma for the nth person. We construct the mu for the nth person, alpha plus beta times the nth person's income, plus their gamma times their age. That gives us mu. Mu, we can add a measurement error with standard deviation sigma, and now we can draw, or we have drawn, from the prior predictive distribution of whatever this outcome is. Sebastian.
Could you like put for in the real gamma statement? Could you could you write normal RNG income comma tau, so then the so you have this increase that's based.
Yeah.
And are you gonna where the amount of noise is based on the income?
So you can have tau be a function of their income?
Yeah. So rather because here you're just making everyone's gamma noisy, and that the amount of noise isn't necessarily related to how much income they have.
But it could be the case that like richer people are more consistent than poorer people in the way in which their coefficient on age is generated. Yes. So you could make tau be a function of income or age or whatever you want. Also, you could write this as gamma equal normal RNG, where everything here goes into the mean, and then there's just tau as your standard deviation, whether tau is a scalar, or tau is something that varies from one group to the next, or tau is something that varies from one individual to the next. All of those totally possible from a Bayesian perspective, and you know, anything that you can draw from the prior predictive distribution, presumably you're going to be able to draw from the posterior distribution once you have data to estimate all these things, inclusive of tau and all the gammas and all that. Becca.
So if you're adding noise where the mean of that noise is 0, what is the purpose of that, given that you're just going to do simulations and the expectation of the coefficient will be, like, the expectation of that will always also be 0?
So yes.
What's the point of adding noise if you're just going to keep something where the mean?
Right. Well, again, ultimately, we're going to be estimating the posterior distribution of all these things. And it's entirely possible that the posterior distribution of, you know, gamma or whatever, this is really just a statement of our priors. And the posterior distribution can deviate from that. But even so, I would argue that this is a more realistic data generating process, because you're not imposing a pretty dogmatic assumption that the coefficient on age is a deterministic linear function of income. Like, that would be weird if, you know, kind of the same way you're thinking of gamma as being kind of like an outcome variable. It's a linear model within a linear model. It'd be weird if you said, okay, my outcome is an exact linear function of my predictors with no error. Similarly, it's weird, albeit entirely common, for people to say, okay, gamma is an exact linear function of income. No deviation in the coefficient on age for two people who have the same income level. Whereas a more realistic thing might be to say, okay, there's a roughly linear relationship between income and the coefficient on age, but it's something that has fundamental noise in it. And I want to be able to allow for that when coming up with my predictions, and having additional noise in the coefficient on gamma is going to percolate down to additional variation in my prior predictive distribution, and additional uncertainty in my priors is going to percolate into my posterior distribution for all of these things. And so when you look at what most people do when they're estimating interaction models, with this rather dogmatic assumption that the coefficient on age is an exact linear function of income, the conclusions that they get out probably have more precision and more certainty than what could be justified, because they basically said, I know for sure the coefficient on income is the exact linear function of age, when they don't know that for sure by any stretch of the imagination. It's just that's what their software permits them to do. Stan permits you to do basically anything you want, and you should want to do models that are realistic. So just to sort of think again about the frequentist perspective on these models with interaction terms, they're very easy to include in software that does frequentist estimation just by conditioning on age and income and the element-wise product of income or age, or at least for the first model that we did. But just because it's easy to put into the software doesn't mean it's easy for people to get the correct interpretation of the coefficient of income times age. So that is gamma 1, and it leads people to basically, you know, car crashes in their mind of thinking, well, gamma 1 is the expected difference in, you know, the outcome between two people that, you know, have the same income and age, but they differ by 1 on the product of income and age. Like they were trying to interpret it like a regular regression coefficient in a flat model, ignoring the possibility that it's impossible for two people that both have the same income and both have the same age to differ by 1 unit on whatever the product of income and age is. It's not even really readily possible to think about what are the units of the variable that's income times age. It's like dollar years. How are we supposed to think about that coefficient? But if you think about it this way, that's not commented out, in the context of a generative model, it is pretty clear that you've made an assumption that the coefficient on age, gamma, is a linear function of the person's income, and gamma 1 is the slope of that linear relationship within a linear relationship. And so you're less likely to get confused, even though both of these forms imply the same likelihood function. But having a generative model makes those assumptions explicit, and you're less likely to get confused by your own assumptions. And when you make those assumptions explicit, it ought to dawn on you just how restrictive it is to say, okay, someone's coefficient on the age variable is an exact linear function of income, so that two people who have the same income have exactly the same coefficient on age. And while it's technically possible to estimate the latter model, it's called the one that has noise in the relationship between the coefficient on age, to use a so-called random coefficient model to estimate the one where the coefficient on age is a noisy linear function of income. But that is a difficult thing to do well from a frequentist perspective, and it's very rarely done. You don't see a whole lot of articles and journals and things like that using this what frequentists call a random coefficient model, because it's difficult to do well. And maybe some justification for that comes from the fourth source of uncertainty that we talked about early on in the semester. Does the software that you're using to estimate these things work as advertised for your particular data. And if you have something like a random coefficient model that really requires, you know, millions of observations in order to get the parameters estimated very well, then, you know, maybe you don't want to do one of those models, or maybe you do want to do one of those models. You just don't want to use Frequentist software to do it because it doesn't work so well. So frequentists, or people who use frequentist methods, will typically limit themselves to interactions with group level indicators rather than interacting, you know, multiple continuous variables together, or adding noise to a continuous coefficient on a continuous variable. If you just have these sort of group level indicators, what race are you, what state do you live in, you know, interactions with dummy variables, then it's easier for frequentist software to find, you know, the mode of the likelihood. And that's what you typically see people doing when they use frequentist software to estimate models like this, with sort of group level structure and group level interactions to it. In order to understand this stuff well, we have to introduce another concept from matrix algebra known as the Kronecker product. Those were mentioned briefly in the matrix algebra reading. They're distinct from the scalar product of scalar algebra and the matrix product in linear algebra, but they have sort of a combination of both. So unlike matrix multiplication, where the number of columns in the leftmost matrix has to be equal to the number of rows in the rightmost matrix, a Kronecker product is well defined between two matrices A and B, irrespective of what their number of rows and number of columns are. So the Kronecker product between a matrix A that has m rows and n columns, Kronecker multiplied with a matrix B that has p rows and q columns, the resulting matrix is going to have mp rows, so the product of the number of rows, and nq columns, which is the product of the number of columns in the two matrices. And the elements of the resulting matrix have this block structure where you take every scalar in the matrix on the left and multiply it by the entire matrix on the right, and then stick it into the corresponding box of the resulting matrix. So we take the top left element in A, which is A11, multiply it by the P by Q matrix B, and then the whole top left block of P rows and Q columns results in B scaled up by A11. And then we do it next to that for A12, and we do it below that for A22, all the way down to the bottom, where we take the last scalar in the bottom right of A, multiply it out by B, and fill in the last P by Q block in the resulting matrix. And so that is pretty straightforward, although you don't see Kronecker products as much as you see other operations in matrix algebra. Often it's going to be the case that either A or B is going to be some matrix that has special structure, like diagonal or maybe even identity matrix. And so if A is the identity matrix, then a lot of the scalars in A are 0. And you have 0 multiplied by B, and that's just going to be a block of zeros in your matrix. So a very common construction is identity matrix times covariance matrix. And that results in a big matrix that has a so-called block diagonal structure. It's not exactly diagonal because some of the off-diagonal elements are non-zero. So like the 1, 2 element of this matrix is going to be non-zero if the 1, 2 element of sigma is non-zero. But sort of down the diagonal, we have clumps of non-zero values, but away from the diagonal, we have blocks of entirely 0. And this construction here, identity matrix times something, is one that is going to come up in hierarchical models. Stan actually doesn't have a built-in function to do a Kronecker product. R does. but it's easy enough for you to write your own function, and it looks a little something like this. So you make a matrix here I call it AOB, which you're going to return at the end, and you initialize it to have number of rows as the product of the rows of A and B, and number of columns equal to the number of columns of A and B together. You need to keep track of the row position and the column position where you're inserting stuff into the matrix that you're going to return. But you just loop over the rows of A, loop over the columns of A, and you stick into the corresponding block of the matrix that you're going to return at the end. The scalar A and the ij element multiplied by the entire matrix B, you just need to stick that into the corresponding block, which can be composed by using the colon operator in stan, which works much the same way as the colon operator does in R, to give you a sequence of integers from here to there, which defines the block in the big matrix that you're going to return at the end, where you're sticking the product of Aij and B. Once that happens, you need to update your position of where the first column is. Once you get out of the inner loop, you need to update your position as to where the next row is and reset the column position back to 1. But anyway, now we have a function that can do a Kronecker product and return out the big matrix at the end, which just corresponds to this relatively simple algebra. The only difficulty in this function is figuring out the indexing to put, you know, A, 2, and B into the right spot in the overall matrix that you're returning out at the end. So you can just basically copy that Kronecker product function if you ever need to use it. So having the Kronecker product enables us to think about estimating so-called random effects models using a frequentist estimator known as generalized least squares. And so this is going to return a matrix of point estimates. It's going to have S rows. We're going to have a new argument, J, which indicates sort of the number of groups that we partition our data in, mutually exclusive and exhaustive groups. So J might be 50 if we're thinking about the 50 states. J might be, you know, 100 if we're thinking about the 100 counties in North Carolina, some number of groups. And then we have an integer array, n, which tells us the number of observations there are in each group. So the length of n here is going to be equal to j. In general, you can have different numbers of observations per group. That makes the coding a little bit more difficult. So in this example, I'm assuming that all j groups are going to have the same number of observations in them. We have a matrix X of predictors. We have a vector beta, which serves as the coefficients on the columns of the matrix X. We have a standard deviation of the errors in the outcome variable sigma. And we have a standard deviation in how much one of these parameters is going to differ from group to group. That'll be tau. And we'll talk about that in a second. So we make mu, which is the vector of conditional expectations, just x times beta. Let's skip all this stuff for a second. We'll come back to it. This all pertains to how we're doing the estimator. So first we want to get straight on how this model thinks of the data generating process. So let's jump to here. We're going to loop over the S simulations that we want to do. We'll initialize pause to 1 to keep track of what position we're in. And we'll initialize a matrix Y for our outcome, whose size is equal to the sum of n. So the total of all observations across all j groups. That's initially filled in with NaN. So we need to fill it with something before we can do any sort of an estimator. So now we're going to loop over the J groups. And the first thing we're going to do for the Jth group is draw A from a normal distribution with center 0 and standard deviation tau. And then we're going to use that value of A in a loop from 1 up to the number of observations in group little j. So this, by the way, assumes that the observations are sorted by group. So all the observations in the first group come first, then all the observations in the second group, etc., all the way down to all the observations in the jth group. And then we're going to fill in y as the corresponding conditional expectation based on that observation's x's, plus a draw of the error from a normal distribution with expectation A and standard deviation sigma that we passed in from the outset. So that will build up y for each observation in the jth group. We increment our position, so the next time through the loop, we're talking about the next observation. And when we've done both of these loops, looped over the groups and looped over the observations with in the group, we have an entire vector that's been filled in with numbers. And then we can use that vector y to try to, in conjunction with some estimator of the parameters in the model. So does everybody understand what I did here from like this line to this line? Stephanie.
What was vector sum and y doing? I missed that.
Right. So y is the outcome vector. Sum of n, since n is an integer array that indicates the number of observations within each group. So sum of n is the total number of observations across all j groups. And so if I have like 100 people from each of the 50 states, then the sum of n would be 5,000. Daniel? No? Anybody else have a question about like these lines here for how the data are assumed to be generated under this model? But you should have a question. Namely, why are these freaking frequentists drawing A from a normal distribution when the entire point of frequentism is that, you know, all these parameters, beta, sigma, tau, etc., are taken as given? We're getting the conditional distribution of the estimator conditional on the parameters, and you can't use, you know, distributions like the normal or whatever to describe your beliefs about a parameter such as A, which is the expectation of the errors in the jth group, or you're just being subjective. Science, if not all of humanity, will crumble if you introduce your beliefs about parameters into a model. And so do frequentists say, well, you know, the entire frequentist agenda since Fisher that's been going on the last 100 years is wrong? No, they do not do that. What they instead do is say, no problem, A is not a parameter. And technically that doesn't make any less sense than the rest of the frequentist agenda. But for some reason, this bothers me more than any other aspect of it. And so basically the semantic game that frequentists are playing here is, well, A is not a parameter, because if you were to do this study over and over and over again, select J groups from some population of groups, and then simulate the data like this, every time you repeat the study, the members, indeed the group labels, change. So the classic example of this in like educational testing, where like the federal government, we want to do a study on students. So we'll take a random sample of J schools, and then within each of those schools, we'll take a random sample of students, and we'll like ask them questions and make them take tests, and then we'll do regressions and stuff to see like what makes students learn better and stuff like that. But if we repeated that study over and over and over again, each time the schools that we drew in the first stage would be different. So like one time we might draw this school over here on Amsterdam and 124th. And then the next time we do the study, that school at Amsterdam and 124th is not in the study. Some other schools are. And so the identities of the schools change every time that you hypothetically do the study when you repeat your research design over and over and over again. And because the identities of the schools change, those are random. And consequently, the expectation of the errors associated with those schools changes every time. And so that's a random variable. And so A, it's not really a parameter, it's part of the error term. And you're allowed, indeed encouraged, under frequentist dogma, to make assumptions about the error term. You just can't express your beliefs about the parameters. And so it's essential that you distinguish what is a parameter and what is part of the error term, so you know where to make your distributional assumptions about. And so you can make any assumption you want as long as you say the thing that you're making an assumption about is part of the error term. But you can't make any distributional assumptions reflecting your beliefs about beta, for example. And that is the distinction, an extraordinarily nuanced distinction that frequentists are drawing. And it's a distinction that is completely lost on 99% of the people who are using frequentist estimators to estimate the parameters of a model like this. But before we go on as to how we might estimate the real parameters, beta, etc., are there any questions about, are there any questions about those lines? Sebastian.
This isn't exactly about those lines, but like other people's classes that modification or interaction terms as being like just like statistical once or reducing, sorry. But just sort of, well, this in order to have the correct error rather than being inherently the process of interest, right? So
right.
You have schools who say we have to include a random effects because that's what we do to account for this as a problem rather than we are interested in the fact that like inherently our model is better.
Yeah, that's one aspect of it. So if you are a parent who has an elementary school aged kid, you might very well want to know what is the expectation of the error term for that elementary school on Amsterdam and 124th, rather than caring about, is the distribution of error terms across all schools normal, which is what the frequentist statistician ostensibly cares about, because the frequentist statistician can't estimate these A's consistently anyway. And the reason why a statistician can't estimate those A's is because they're not parameters. And you can only estimate parameters. But substantively, yes, we may very well care about the school specific, the group specific, the individual specific unknowns. So leave.
What I'm so confused about is like in that perception, I mean that's like you mentioned before, but like if we then say there's like a full population, like the super population, like all schools in the United States, then like we group them by something, like they are like different groups, and then but then A is like clearly not like a random variable, right? Like if we could use the whole population at always. That's what I'm saying.
Yeah, there's for mathematical reasons, we're sort of thinking of the schools as being an infinite population, when in fact there is a huge but finite number of schools. So in principle, we could exhaust them, but the math of doing the estimator works easier if we consider all schools to be a continuum of infinite continuum of schools that do or could exist. Now, as soon as you sort of make a frequentist sanctioned estimator, people tend to use it for situations in which there is not an infinite number of groups. So they'll use a random effect model, one for each of the 50 states. There's only 50 states. There's only a certain number of races that are kept track of by the census, etc. But once it's sort of possible to do in one circumstance where it might make sense, there's a whole flood of people who want to use that estimator in situations where it doesn't make sense, according to the justification of this. And one estimator of a model like this is the so-called generalized least squares. And all this matrix algebra stuff up here is just a precursor to that. So you take the Kronecker product of an identity matrix, and this matrix here, the square of tau, which is the variation in the error expectations across schools, and the diagonal matrix, this should be sigma, I think. One of these should be sigma. Anyway, a diagonal matrix with the error standard deviations, Kronecker product, those two things together, and you now have a sum n by sum n covariance matrix of the errors. And so the frequentist way of thinking about this, as Sebastian was alluding to, is that we have this nuisance that the errors are correlated within school rather than all students being conditionally independent. And so if you then multiply your matrix X by the Cholesky factor of that error covariance matrix, so this m divide left try low is the same as L inverse times X, where L is the Cholesky factor of that covariance matrix, then you get a new X that you can then do, new X transpose, new X inverse multiplied by new X transpose to get the left-hand side of the thing on the left. And then you're essentially doing OLS with the transformed variables X underscore and what you might think of as Y underscore, this Cholesky factor inverse multiplied by Y. So transforming your X data and your Y data by the Cholesky factor of the covariance matrix of the error, group-wise error structure. You can do OLS on this transform data, and you get an estimator of the coefficients beta. You do not get an estimator of sigma or tau, but you do get an estimate of these coefficients beta. Now, GLS is not a particularly useful estimator for reasons which we'll see in a second, but there is an estimator. You can also do this by maximum likelihood, but then you have to do sort of numerical maximization. Not that difficult to do, but difficult to depict in a STAM program. This generalized these squares gives you a so-called closed form solution for the estimator of beta. So we can use the so-called sleep study data set, a data set where they did an experiment depriving people of sleep for some number of days and then measuring their reaction time when they threw stuff at them. So we create an X matrix based on the intercept and the number of days that you've gone without sleep. We do 100,000 observations. People were divided into 18 groups, or there were 18 people, and they each had 10 things thrown at them, 10 measurements of their reaction time. We pass in X. We pass in a vector of coefficients 1 and 2 for beta, 3 and 4 for sigma. Expose this to Stan. Estimate the expectation of the sampling distribution of our estimator for the coefficients, and it comes out very close to 1 and very close to 2 on average. So if we average down these 100,000 on each of these two columns. So we have successfully gotten an unbiased estimator of the coefficients beta. And generalized least squares in this circumstances is the unbiased estimator. In fact, it is the best linear unbiased frequentist estimator when the errors are correlated within group. You might have heard that OLS is the best estimator, but that pertains to the situation where there's no group-wise structure to the errors. Doing this transformation and then doing OLS actually results in the best linear unbiased estimator when you have errors that are correlated within each group, each school, each state, whatever that may be. But it is worth reflecting on just how deceitful it is to say that this is the best linear unbiased estimator. Okay, unbiased, that has kind of a special meaning where the expectation of the estimator equal to the thing that we're estimating. We know what linear means. Best is another thing that actually means something very specific. It means the smallest variance among estimators that are both linear and unbiased, and that smallest variance refers to the sampling distribution. The one thing that we can be objective about, that being the conditional distribution over data sets that have been randomly sampled from the same population of an estimator given the parameters. And so all this nonsense about a best linear unbiased estimator leaves off the fact it's best in the sense conditional on the parameters that you are trying to estimate. And so if you don't know what sigma is, the standard deviation of the measurement errors, and you don't know what tau is, which is the variation in the expectation of the errors from one school to the next, you can't construct this Cholesky factor, and thus generalized least squares is completely infeasible. It's only feasible if you're given what sigma and tau are. Now, fortunately, some clever economists have come up with an estimator known as feasible generalized least squares. Although feasible generalized least squares, although feasible, not unbiased, doesn't have any justification at all in finite samples, only asymptotically. And among all frequentist estimators, feasible GLS is pretty much the worst, in the sense that if you do with a finite sample, you never get asymptotically, or you never get a normal sampling distribution when you only have a finite number of observations, finite number of groups. And so the best linear unbiased frequentist estimator happens to be completely infeasible if you're not given what frequentists take to be given, which is the parameters that you're trying to estimate. If you're not in that situation, then you have to resort to these, like, you know, secondhand approximations known as feasible generalized least squares. And then the estimates that you get out do not resemble in properties the thing that justified generalized least squares in the first place. And that happens with a lot of these frequentist estimators. Now, you can do all this by maximum likelihood, and it's a little bit better. It's still not unbiased. And so people have come up with improvements to the maximum likelihood estimator that regularize or penalize the estimates, and those work a little bit better. But then they no longer have the properties of a pure maximum likelihood estimator, which is what Fisher and other people of his days used to convince everybody that they should be doing everything by maximum likelihood. Certainly not any, you know, Bayesian stuff. So last thing today, I want to go through sort of a restatement of hierarchical model kind of in general. So when we think about the coefficients in the J group, before we were just having this sort of single a parameter that varied from one group to the next. But in general, the coefficients could vary from one group to the next. And we want to compose the coefficients in the jth group as an overall beta vector plus some deviation in that is specific to the jth group. And we can collect all the j-specific coefficient deviations and stack it all into a vector and have a corresponding vector of u's that has the same structure. And we can write a hierarchical linear model in the following way. Y is equal to x times beta plus z multiplied by b, where z is going to be a sparse matrix that basically contains the interactions between several, maybe all of the columns of x, and these dummy variables for what group this or that observation is. Dummy variable for what school, you know, person number 42 is in, etc. Plus a measurement error in the outcome, epsilon. And we can equivalently write that as x times beta plus z times the Kronecker product, actually, between an identity matrix and the Cholesky factor of the covariance within groups, multiplied by one of the elements of the U vector, multiplied by sigma, which is the standard deviation of the errors. And so there's two ways that you can think about an expression like this. From a Bayesian perspective, the conditional mean of y given x and z is this whole thing here. When frequentists look at the same equation, they say the conditional mean of y given x only is just this part here, x times beta. We're not conditioning on z. And then conversely, when Bayesians think, okay, well, here's my conditional expectation, here's my measurement error at the individual level, frequentists are thinking about this whole term here as constituting the error term or a vector of errors for a particular individual. So whether you look at this equation from a frequentist perspective or a Bayesian perspective, basically it consists of how you chop up these three things into two groups, two of which have to go into the, well, two of which have to go into one thing and one of which has to go into the other. Frequentist just takes this part to be the conditional mean, takes this part to be the error. Bayesians take this whole two terms here to be the conditional mean, and what's left over is the error. So Bayesians are conditioning on x and z, frequentists only conditioning on x and letting this z business go into the error term, which induces dependence within group in the errors. Rashika, you had a question? Yeah, so Z is a matrix that has interactions between predictors X and the group level dummy variables. So if you have income and then you have sort of what state you live in, there's going to be a column of Z for income multiplied by the dummy variable, do you live in New York? So it'll be income for everyone who lives in New York, and it's 0 in that column for everyone who isn't in New York. U relates to B as follows, using the same construction that we were talking about last Thursday, where if you have a multivariate normal distribution, you can write that as Cholesky factor times independent standard normals. So U represents something that both Bayesians and frequentists believe to be independent standard normal, and you're multiplying it by the Cholesky factor of its covariance matrix. So both Bayesians and frequentists are making the same assumptions about each of these U vectors, but frequentists are integrating the U's out of the likelihood, and then they choose the real parameters or estimates of the real parameters, beta, sigma, and L, to maximize their likelihood function, which is going to be multivariate normal of size n. Whereas Bayesians are conditioning on x and z, and conditional on both x and z, the observations are assumed to be conditionally independent, and thus the likelihood from the Bayesian perspective is just n univariate normals, or all univariate normals for each of the observations conditionally independent multiplied together. So whether you condition on z or let it go into the error term determines whether you're approaching this from a Bayesian or frequentist perspective, and it yields different likelihood functions. So you can estimate these parameters by maximizing the likelihood, or you can estimate these parameters and the b's by, doing Bayesian approach, MCMC, to get the posterior distribution of all the unknowns, sort of irrespective of whether you think B is part of the conditional expectation or the errors. So we've run out of time today. We'll have to pick this up on Thursday, where we'll go over the homework, and we'll also get into how you would estimate some of these hierarchical models using our standoff.